Assalamu alaikum dear students. From today we are going to start the lecture series of partial differential equation. If you remember before the vacations and even after the vacations we had started reading partial differential equations, and on the WhatsApp group after the global pandemic COVID-19 we had eventually started linear first order partial differential equation. I had given you the video tutorial regarding first order partial differential equations, which is actually our second module. So regarding linear first order partial differential equation, we have covered the topic, and video lecture is with you. I had given you the link. You can go and study that lecture. From now on we will be starting the lecture series regarding partial differential equations, and today's topic is quasi-linear first order partial differential equation. So let's formally define what do you mean by quasi-linear partial differential equations. I have written that equation 1 is known as quasi-linear partial differential equation. This is actually similar to the linear one. In linear partial differential equation we say that the coefficients a, b, c are only functions of x, y, and there is no z component. And if you can change this form into the following, that a, b, c are indeed now coefficients of x, y, z. You can take c on the right hand side or on the left hand side, doesn't matter. So this now new equation 1 is known as quasi-linear first order partial differential equation. Today we will try to study how can we solve this equation, but before that just name the solution of this equation, that is z, which is function of x, y. So in general z is called the solution. For example, how you can elaborate z? Z can be any function of x, y, like z is equal to x square plus y square. But then you can take right hand side to the left hand side or left hand side to the right hand side and form a new solution, which is f capital of x, y, z in three variables, and this is equal to 0. We need this form of solution, so I am just explaining you how can you write z equal to z of x, y in terms of f of x, y. So this will be our solution, and on the lecture notes I have written that f of x, y, z equal to z minus z, which is equal to 0. So now this is your solution, and z minus z, you now understand what do you mean by this. This is your required solution, and writing the form in that writing the solution in that particular form is known as implicit form of the solution. What is the benefit? You will eventually understand that writing the solution in that form will make it easy to understand the methodology to solve quasi-linear first order partial differential equation. To move on, let's define what do you mean by gradient. I have defined, but you also know from differential geometry and calculus 3 that gradient is a vector field at each corresponding point x, y, z gives you a vector in the space, and this is defined as partial f over partial xi, partial f over partial yj, and partial f over partial x zk. But geometrically, please go to your differential geometry course or a fine geometry course. You will understand the gradient is normal to the integral surface of. So to whom the gradient vector is calculated, that vector will be regarded as a normal vector to the surface at each point x, y, z. What is the benefit of that? You will understand just after 2 minutes. So let's take right hand side to the left hand side, which I have already taken in that mathematical tab. You see that azx plus bzy minus c equal to 0. So if you take that right hand side to the left hand side of equation 1, now you can write this left hand side as the dot product of two vectors. One of them is abc and the other one is zx, zy and minus 1. Because dot product is defined as the sum of multiplication of corresponding components of two vectors. So a will be multiplied by zx and b multiplied by zy, and c will be multiplied by -1. So eventually you will get the right hand side, the left hand side. Now just imagine and concentrate your whole thinking on that particular point, that you have dot product equal to 0. If you have dot product equal to 0, abc dot zx zy -1 equal to 0, mathematically you understand that both vectors have to be perpendicular, or second case can be that either of them is 0. But we are taking abc non-zero, otherwise everything on the equation 1 will be 0 equal to 0. So we are not taking that case. abc, suppose that they are non-zero, and gradient vector which is normal is also not a null vector. So the only case possible is that both vectors are perpendicular. So if two vectors are perpendicular and you know the property of one vector which is gradient, and this is normal to the surface. Since this is normal to the surface but eventually this is also perpendicular to ABC, so you have to think about what is a vector which is perpendicular to a vector indeed which is normal. So if a vector is normal, the only vector which is perpendicular to normal is tangent. You understand from the geometrical aspect that if you draw a tangent, then normal and tangent are always perpendicular. So since geometrically gradient is normal vector, the vector which is perpendicular to normal vector has to be tangent vector. But since you are dealing with surfaces, and on the surface you don't talk about tangent vector, you talk about tangent plane. So it is better to write in the language that ABC is a tangent vector which lies in the tangent plane of the integral surface. Because if you can imagine a surface or a football, you understand that any plane, or if you imagine, you can suppose a paper on the surface of football, this will be regarded as a tangent plane, and any line lying in the plane will be a tangent line on the surface. So actually on the curve we have one tangent at a point, but on the surface we have many tangents on one point. So eventually we talk about tangent plane, not we talk about tangent line. So actually it is better to say that ABC is a tangent vector which lies in the tangent plane on the surface z of xy. So at each point xy, now it is a question which can be asked, that you have a tangent vector, right? Just imagine that lectures of 3 and 4 of module 1, where there was a one question about integral surfaces. So okay, if you remember this definition on the page, yes, integral curves for a vector field. So let V be a field, be a vector field defined in some domain. So V cannot be 0, number 1. Number 2 is that PQR, the functions are continuously differentiable function. So a curve is integral curve of the vector field if V is tangent to C at each of its points. You have a vector field which is named as ABC in that lecture. So now ABC is a vector field because at each point you are getting a vector. Okay, now concentrate your mind on the following thing, that you have a vector field. So you are now supposing the vector field not ABC, it is not PQR, it is ABC. At each point you are getting a vector. Okay, okay. Okay, so at each point you are getting a vector, and now this vector field can have a curve which can be called, you name that curve C. This curve, what we are trying to define is curve which is characteristic curve. So how to define? Actually in that lecture, if you go back, this curve is known as characteristic curve because at each point at each point of the vector field. For example, you put a, b, c instead you put okay, you suppose that you are taking the point 1 2 3. Okay, so at 1 2 3 the vector will be what? The vector will be a of 1 2 3, okay, b of 1 2 3. You don't know what is a, what is b, what is c, and c of 1 2 3. Okay, so this will be your tangent vector. Okay, now at that point 1 2 3, if this vector is also tangent to the curve, okay, curve is also on the same domain. The domain for the curve is r cube, okay, or any subset of r cube. You don't have to be precise. Any omega domain. I think we had taken suppose omega as your domain. So any subset of that domain. Okay, so imagine that a curve is also lying in the domain r cube, omega, which is subset in r cube, and your vector field also has a domain omega. If at each point of the omega, the vector which you are getting from the vector field, which is a of 1 2 3, b of 1 2 3, in that example c of 1 2 3, the vector which you are getting from the vector field is actually tangent to the same point 1 2 3 to the curve c, then that particular curve, and this happens for all points, and this happens for all points in omega. Okay, so then that particular curve is called characteristic curve, because this curve actually describes the characteristics of your vector field. You are taking point 1 2 3, not 1 2 3, you are taking point 7 8 9. At 7 8 9 you will get a vector. This is one thing. And at that 7 8 9, if you have a curve c at that particular point 7 8 9, the tangent vector is also a of 7 8 9, b of 7 8 9, and c of 7 8 9, then that particular curve is known as characteristic curve. So at each point in the domain you are getting the vectors, and these vectors are also tangent vectors to the same point on that curve. So that particular curve will be known as characteristic curve. You can talk about characteristic curve for any vector field which is non-zero and which has components which are C1 functions. If you remember that our vector field is ABC, and we have supposed in quasi-linear partial differential equation that they are C1 functions, which means that they have continuous partial derivatives which exist at each point. Now for that you can talk about characteristic curve, and that curve in parametric form written as x of t, y of t, and z of t. You don't know how to calculate, but the name is x of t, y of t, and z of t. This is your characteristic curve which depends upon the characteristics of ABC. Remember that ABC are components of not any vector, these are components of tangent vectors. Okay, now tangent vector, how can you calculate? These are characteristic curve, and how can you calculate the direction? Remember this thing that you had defined here. What do you mean by a characteristic curve? That a curve is known as the integral curve of the vector field if v is tangent to c at each of its points. So at any point, if you are getting tangent vector vector from the vector field, this vector is tangent to the curve c. At any point you are getting the vector from like that. At any point you are getting the vector. For example, at 1 1, what will be the answer? 1 minus 1. At 2 3, what will be the answer? 3 minus 2, 0. So at each point you are getting a vector, but that particular vector is also tangent to these curves. Then this is called integral curve, and this curve has to be precisely equal to circle. Similar to that, since the components of integral curve by definition are components of tangent. So in order to see the direction, you have to take the derivative of that curve. So the tangent vector will have component x dash, y dash and z dash, but these must be identically equated with a, b and c, because a, b, c is a vector field which has integral curve whose name is capital C and whose parametric form is given as in equation 3. So identically these has to be equated with the tangent components, and dx over dt must be a, and dy by dt must be b, and dz by dt must be c. So these are the components of tangent vectors and the integral curve, and solving this system will give you the integral curve. Now just concentrate on one thing, that equation was one was quasi-linear partial differential equation, and in order to solve quasi-linear partial differential equation, eventually you understood that you have to solve the system 4. Now system 4 is system of 3 ordinary differential equations. So solution for ordinary differential equation system exists for 3 equations if your right hand side is smooth function. I have written that a smooth function and sufficiently smooth function, that which means that derivative at each point x0, y0, z0 exists and is defined, and a, b, c are continuous as well. So the initial value problem, I have not defined the initial value problem for a quasi-linear partial differential equation, but any initial value problem will have solution which exists and also unique. But this is, I have written only for you to understand and to build your knowledge that this system has actually indeed guarantee. This is the guarantee that the solution for that system exists, because ordinary differential equations has the guarantee that the solution will exist if a, b, c are smooth functions. We know that a, b, c are smooth functions, so if the system of 4 has solution, equivalently equation 1 has solution. I have written that in the following manner. Look, you had system 1, now identically this is if and only you have the corresponding system of 3 ordinary differential equations. Now from ordinary differential equation knowledge, since right hand side is smooth, so solution exists, and initial value problem has unique solution, which is not the topic for today. We will study this topic later. And now how can you solve? Actually the main problem is that how can you solve system 4? For example, you have 2 linear simultaneous equations in 2 unknowns, you have Cramer's rule, you have any other A inverse formula from linear algebra, but this is system of ordinary differential equation. Is there any rule to solve this? If the answer lies into the fact that what is the difficulty level of the question. For example, this is a theorem which we will be using. I am not going to prove that theorem, but you have to understand the language of that theorem. So the general solution of the quasi-linear first order partial differential equation, which is equation 1, will have solution in the following form. Any relation, f is any relation of uv equal to 0. What are uv? uv indeed are solutions or in the form u is equal to constant c1, v is equal to constant c2, and u and v are actually solutions of this system. dx over a is dy over b is dz over c, which is actually the answer of this system. Dx over dt is a, because you can equate dt and the answer will be dx over a equal to dy over b is equal to dz over c. They are both identical. So system 4 and 5 are identical, but you can say that this system has 2 solutions, because it can have many solutions, but we are dealing only 2 independent solutions. So you can equate first 2 sides and then you can equate second and third side. You will get 2 solutions, and these are named as u and v, and any relation between them is your solution. This is the theorem, but I am not going to prove that theorem, yet I am going to give you some examples regarding this theorem. So imagine that you have this quasi-linear partial differential equation, and this quasi-linear partial differential equation is in the following form: a is x, b is y, and c is z. Okay, So the corresponding associated system of equations is dx over a is dy over b is dz over c. Now as I had told you, first of all just concentrate that can you solve it like that. First two equations are equal and the first two relations equal, we get dx over x is equal to dy over y. Second main step is that you have to understand, can you integrate both sides? Is it a separable equation? If it is separable, I mean to say that differentials of x and any polynomial in x or function in x is on the left hand side, differential of y and y variable relations are on the right hand side, then you can integrate both sides and the answer will be this. In the theorem, this is called, if you go back to the theorem, this is called u. Any u or v you name, this is up to you. This is one side and this is called u. Similarly, you can equate second and third. You can integrate both sides and you can get z over y is c2. This is called v and any relation of them is equal to 0. This is your required solution. Now what I am trying to explain you what this relation can be. This relation can be x over y or u plus v equal to 0. This relation can be u minus v equal to 0 or any other relation which you are going to understand. But in general we write f of x uv equal to 0. So now this was one example, but second example is more critical, more difficult. You have this type of equation and you can write associated equations as dx over a is dy over b is dz over c. In that equation system, how can you solve? Can you equate two sides and the second and third side? Can you easily get the solution? The answer is no, because now you cannot apply any ordinary differential equation technique. Because look, if you equate two sides, you will get dx over a is dy over b. Z and z are cancelled because you had z on both sides. Now if you can transform this as m dx plus n dy, you can solve and the answer will be some small f. I don't know what will be the answer, but I'm supposing this is f and the answer will be c1. This can be u. You can suppose this as u. But for the other side, if you suppose second and third are equal, differentials of y and differentials of z are involved in the relation. But this means that if you are taking exact differential equation technique from ordinary differential equations, there should be only two relations of y and z, not x. But look, we have involved x also. This will create a problem. That is why you cannot make this exact also, because there is x here, or you cannot suppose that equation is exact and you can solve. So what you can do is that you can apply the method 2 here, in which we had to suppose P1, Q1 and R1 and P2, Q2 and R2 in order to solve the system of ordinary differential equations and in order to find out the characteristic curve, integral curve, sorry. So now what you will do, that you have to suppose what is P1, what is Q1, what is R1. In this case, don't be hesitant. Here we are dealing with ABC, not PQR. So you can suppose what is A1, what is B1, what is R1. For that and for that B1 and for that C, what is C1. So you have to suppose what is A1, what is B1 and what is C1. Very easy formulas. For example, just imagine P1 Y. We have taken, sorry, A1 or P1, they are both similar, is Y, and B1 is X or Q1 is X and R1 is Z or C1 is Z minus Z. So if you suppose that, then PP1 plus QQ1 plus RR1 will be equal to 0, and this has to be 0. You have to suppose P1, Q1 and R1 such that PP1 plus QQ1 plus RR1 have to be 0, like that. And similarly other one, P2, Q2, R2 or A2, B2 and C2. You have to suppose A2, B2 and C2 such that A to A plus B to B plus C to C, this sum has to be 0. If this is 0, what will be the benefit? Look, the benefit will be that theorem says that this is equal to any proportion. This is actually a proportion of two ratios, that this is equal to either dx over p, either dy over q, either dz over r. Similarly, this for p2 or a2, b2, c2, they both are same name, different names of the same thing, is equal to dx over p is dy over q is dz over r. Now if it is equal, if you equate with any side, I don't know, whichever you want, the answer will be 0, because 0 will be equal to 0 divided is equal to multiply by dx over a, or 0 multiplied by dy over b, or 0 multiplied by dz over c. So the answer will be 0. Y dx plus x dy minus dz is equal to 0, and similarly for the other numerator the answer will be 0. So what will be the benefit? Look, the benefit will be that doing in this methodology, you can merge this left hand side into one exact differential. It is not derivative, it is exact differential. Actually we are dealing with exact differential equations. This is another technique to deal with exact differential equations. So look, y dx plus x dy is actually derivative of xy. If you take derivative of xy, what will be the answer? X dy plus y dx. This is there. What will be the answer of that? That will be z square by 2. Because if you take the derivative of z square by 2, the answer will be z dz. So you can actually merge the left hand side into exact differential equal to 0. If any function has differential equal to 0 or total derivative equal to 0, it means that the function itself is constant, and this is now your u1 or u. Secondly, if you take this, what is a function whose derivative can be x square by 2? What is a function whose derivative can be minus y square by 2? What is a function whose derivative can be minus z square by 2? So the total derivative of this summation or sum of function is 0. It means that the function itself is constant c2, and that will be your v in the theorem. So the answer, or hence you can write the solution of equation 1 is f of uv equal to 0. That was there, f of uv equal to 0. This is your answer. So this is very easy to talk about the solutions of quasi-linear partial differential equation if you have methodology 2 very carefully understood. So I will suggest that this lecture was delivered before the vacations, and also I had made the video lecture regarding this, which is uploaded on LMS, on the online courseware of Khwaja Farid University, and also on the YouTube link which is on LMS. So if you go back and you can understand, you have to understand the methodology, method 1 and method 2. This is actually in the lecture notes which I have typed in method 2, and also you can use method 1 as well. It is up to you. So this is the methodology from which you can solve quasi-linear partial differential equations, and in the next lecture I will try to explain you and discuss with you the method of characteristics for quasi-linear partial differential equations, but now in the case of initial value problem. There will be some conditions, there will be some constants to be determined, and then you can actually solve the initial value problem. So in the next lecture actually I will try to explain you the initial value problem. You can discuss with me any problem if you have for any particular point which you didn't understood, and in the end I have given you the problems as well. I have explained 2 examples. Now you will see you will have some problems. Don't use the conditions, just try to apply the method and do practice as much as you can, because for the conditional questions I have not given you the lecture. Next lecture which you will see will be regarding these conditions, but up till now you can make practice if you want for the problems regarding quasi-linear partial differential equations. Thank you very much for listening.